Welcome to another tutorial of Proflearn YouTube channel. In this particular video, we're going to talk about matters electromagnetic induction as far as physics paper 40625 is concerned. If you are new to Proflearn YouTube channel, consider subscribing so that once I'm going to upload the tutorial of space physics, you'll be notified. So let's go and dive in so that we can be able to see exactly what you are supposed to do in this kind of a scenario whenever you are given a question on electromagnetic induction. So looking at this, you see we have one of the questions that was tested in one of the year of IGCSE Physics, this Cambridge, and we have a magnet that is suspended, and which means that the magnet can be able to move up and down, can be able to oscillate. But in the process, the fields of the magnet can be able to cut through the coil. So we are asked to describe and explain what happens to the needle of the sensitive galvanometer. A galvanometer is a device which can deflect or which can move when a current flows through. So we're going to say as the magnet moves up and down, the fields of the permanent magnet are going to cut across the coil. And when this happens, when the fields of a permanent magnet cut through the coil, an EMF is induced inside the coil through electromagnetic induction. So this is the process through which electricity is created. When the fields cut through the coil or cut through the conductor, an EMF, electromotive force, is induced inside that coil or inside that conductor. And when there is an EMF, then there is a flow of what? Current. Now the magnet is replaced with a stronger magnet. Now we're going to have stronger field. Then it means the amount of EMF that's going to be induced in this coil is going to be greater. So that means there will be a larger diffraction in this case. Then another possible question that can be asked is whereby you are given maybe we are talking of a coil that is going to be rotated within a magnetic field, and you can see now this coil that we are having here is between magnetic field, and the fields are produced by the permanent magnet. So these magnets that we are having here are there to produce magnetic fields. So if we have a coil that is inside a magnetic field, if you make a mistake, you move that coil, then such that the coil is going to cut through the magnetic field, it means that inside this coil that we have here, we are going to have an EMF being induced inside that coil. And that is how generators are able to generate what? Electricity. So which means that when this handle is rotated, the coil is made to cut through the magnetic field, and then an EMF is induced through electromagnetic induction. So let's see what question was being asked here at this given point. They were asked on the diagram, draw an arrow to indicate the direction of the current. Right? So we are going to use, because a generator, we are going to use Fleming's left-hand rule. Yes? Fleming's right-hand rule. So you are going to place the first finger, second finger, the thumb, such that they are at 90 degrees. So you place them in such a way that the first finger is pointing to the direction of the field. Yeah? And if the coil is moving upwards, the thumb should be in that direction in which the coil is moving. So in that way, the current is going to flow as indicated here, and I used what we call Fleming's right-hand rule in this case. So the current is going to flow in this direction, and on this other side the current will flow down like that. On the diagram draw, we have indicated that, and we're supposed to explain your answer. The field, the direction of motion of the wire, and the induced current are mutually perpendicular, and that is why the current is going to flow in that direction. Explain how the rotating coil in the diagram continuously causes the galvanometer needle to show alternating current. So already we said as the coil rotates, it cuts through the magnetic field, and this induces an EMF or a voltage inside the coil. And after every 180 rotation, the direction of the current that is induced in the coil also reverses or changes, and that is what you are supposed to respond in this particular question. Another question that you'll be asked in that particular exam is about transformers, and you need to understand there are two types of transformers, which include the step-up transformer and the step-down transformer. What is a transformer? A transformer is a device which is able to increase or reduce voltage. So in that way, if we are having a transformer, then you can be able to determine whether it's a step down or a step up transformer by looking at two features. You look at the coil. If you have more coils or more turns in the primary coil than the secondary coil, then this is a step down transformer, because this transformer works in a principle that when AC current, when alternating current flows through the primary coil, is going to create magnetic fields which are constantly changing size and direction. When those fields which are created due to the flow of current cut across the primary coil, then less cut across the secondary coil, then less EMF will be induced in the secondary coil. Because we have fewer turns, then less EMF will be induced in the secondary coil. Explain the operation of the basic operation. Explain the operation of a basic transformer. A transformer is made of what? Coil and a soft iron core, because a soft iron core is easily magnetized and demagnetized. So the basic operation of this transformer is that when alternating current flows through the primary coil, that alternating current creates magnetic fields which are constantly changing size and direction. When those fields that have been created cut through the secondary coil, an EMF is induced in the secondary coil, thus making current to flow. Question number 4, we are having a conductor XY, and this conductor is made to move. When it moves, a current is created through electromagnetic induction. So in that way, we are supposed to indicate on the diagram or on the table below, indicate the direction of the movement of it says that on the table below, tick one box to indicate the direction of the movement of the wire X and explain your answer. So we are told that current moves from X to Y. So you are going to use, because this a generator is generating electricity, so you are going to use basically you are going to use Fleming's right hand rule. So I'm going to hold my fingers like this, such that the three fingers are at 90 degrees to each other. So if I look at the flow of current here, so I'm going to put such that this is pointing from the north to the south, this first finger, and this other finger here is pointing the way the current is flowing from X to Y. So it means my thumb is pointing upward, so it means the motion of this conductor is upwards. So if I check here is to the top, I'm going to select to the top of the page, to the top of the page, to the top of the page. In that case, you try to do it using your right hand rule. But when we are talking about DC motors, we use Fleming's left hand rule in order to predict the direction of motion and rotation of that. So moving to part B, we are supposed to state the observation. State what observed on the ammeter when XY is moved in the opposite direction. It means also the direction of current is going to reverse yeah, the direction of the current becomes goes to act in the opposite, flow in the opposite direction. And also we're supposed to state what happens, or the observation, when it's moved in the same direction but greater speed. When it's moved in the same direction but a greater speed, the current will be in the same direction, but it will be a larger amount of current. So the ammeter is going to show a larger deflection. Part 5, question 5, describe what's meant by the direction of magnetic field. Actually, this is the direction of the force that acts on the North Pole, and it acts from the north to the south. That is for part A. Describe and explain what happens with the beam of electrons. So you see, electrons behave like flow of current, because current flows which is current flow due to the flow of electrons. So if we are having a beam of electrons, then it indicates that is the same as the flow of what? Current. But remember, electrons usually flows in the opposite direction, so we are going to use Fleming's left-hand rule, but the current should be, you should position your finger such that the current finger is pointing opposite direction in which the electron flow, because when electron flow, usually current flow in the opposite direction of electrons. So when you are using Fleming's and left-hand rule to demonstrate that, you have to ensure that your current finger, this one, is pointing opposite to the direction of flow of electrons, and in that way we are going to say the beam deflects into the page, since moving electron constitutes a current. According to Fleming's left-hand rule, this is going to move into the page. In question number 6, the diagram shows a symbol direct DC. On the diagram, we were supposed to draw a pair of arrows to show which coil rotates, which way the coil rotates, and we need to explain the direction. So you can see now in this case here, question number 6, current is going to flow in this direction. So if you use Fleming's left-hand rule, this part is going to experience a downward force and the other end is going to experience an upward force. So in that way the coil is going to rotate anti-clockwise direction. And we are supposed to explain why the electrons flow in the direction as shown. Electrons usually flow in the opposite direction, so when you are supposed to indicate the flow of electrons, it will flow in the opposite direction to current. Why? Because electrons are negatively charged, so which means they are going to be repelled by the negative terminal of the power supply. Explain why electrons flow that way. We have explained that. State the quantity which is induced in the base of the pan, that is electromotive force, EMF, or we can say voltage, is induced in the base of the pan. When current flows through the coil, there will be magnetic fields which will be created, and when those magnetic fields cut across the pan, because a pan is a conductor, then we are going to have an EMF induced at the base of the pan. When EMF is induced, a current is going to flow through the pan, and then thermal energy is going to increase, because we know energy is equals to IVT, current times voltage times time. So do state and explain the effect of the quantity induced on the temperature of the water. Due to the EMF, current is going to flow, and since the pan has resistance, then we are going to have thermal energy produced at the base of the pan, which means that the temperature of the pan increases, which increases the temperature of the water. Yeah, so basically that's what we are going to mention as far as that is concerned. And this is just to remind you that if you have not subscribed to Proflearn YouTube channel, consider subscribing, so that anytime I'm going to do more tutorials, you'll be notified. Also remember to join our Patreon page so that you can be able to access these PDFs that I'm having here, and also to download this worksheet so that you can be able to have it on your end there. So moving on, we have a toy car, a trolley that is running down the slope. And what we are having here, there is a magnet which is attached on that trolley. And we can see that this magnet has got magnetic fields. And remember that when this trolley is running down, basically what's going to happen is that those magnetic fields are going to cut through the coil that we are having here. So as it's going to run down the slope, the fields of the permanent magnet are going to cut across this coil that we're having here. And we have mentioned that whenever the magnetic fields cut across a coil or a conductor, then an EMF is going to be induced in that conductor. So which means that when this trolley passes through here, the field will cut across, an EMF is going to be induced, then a current is going to flow through the coil, then this galvanometer is going to deflect. So the amount of EMF induced, the amount of voltage that is going to be induced here will depend on two factors. Number one, it will depend on the strength of this permanent magnet that we have here. So if we have a stronger permanent magnet, it's going to induce more EMF, so more current will flow, so meaning there will be a larger deflection. Okay, so also if the trolley moves faster, then it means the magnetic field will cut across very fast, then it means there will be a larger EMF which is going to be induced. Let's look at the question that was asked. State and explain what's observed in the galvanometer. The galvanometer is going to deflect. Why is it going to deflect? It's because as the trolley runs down, the magnetic fields are cut across the coil, and an EMF is induced in the coil, which causes the current to flow. And once the current flows, the galvanometer shows a deflection. State and explain. The trolley is now moved. Now we have point A, and then it's moved now to point B. What does that mean? If it's moved to the higher point, it's going to have higher potential energy. And remember, when the trolley is moving down, the potential energy will be converted to kinetic energy. So meaning at this point it will have higher kinetic energy, rather it will be having high potential energy at this point. So when it's going to run across, it will going to run at a higher speed. So it's going to cut across the coil faster, and a larger EMF is going to be induced. So it will show a greater deflection because it will be moving at a higher speed. It will show a larger deflection because it will be moving at a higher speed, and a large EMF is going to be induced. I believe you are getting value from this particular tutorial. We need to move down so that we can quickly run through and get to C. So we have a battery that is being charged here, and this charging system is in such a way that there is an EMF that is alternating current flowing here. So when alternating current flows through this coil, it's going to create magnetic fields which are constantly changing size and direction. So these magnetic fields which are constantly changing size and direction are going to cut across this coil X, and when a field cut across another coil, there is an EMF that is going to be induced in that particular coil. So the question was, explain how alternating voltage is produced in coil X. Remember, these two coils are not connected in any way, but when there is an there is a current, alternating current, this coil, there will be a magnetic field created, and this magnetic field are constantly changing size and direction. When they cut through coil X, an EMF is induced through electromagnetic induction, and that's basically what you are supposed to state in this part. As current flow, AC current flowing in coil Y creates a changing magnetic fields. The changing magnetic field cut across coil X, and an EMF is induced through electromagnetic induction. So you can see these questions will always be the same, but it's only the scenario that's going to change. The explanation is basically the same. So let's talk of a scenario whereby you are given what? You are given here this generator. You are given, sorry, a transformer, and you can see here we have a transformer which has 340 turns in the secondary. In the primary we have 200 turns. So which means this is basically a step up transformer. So explain why there is a voltage between the terminals of Q. Remember, when AC current is connected here, what's going to happen is that there is going to be magnetic fields which are created in the primary coil, because there is alternating current inside the primary coil. Then it means that alternating current is going to create magnetic fields which are constantly changing size and direction in the primary coil. When those alternating current cut across the secondary coil, an EMF is going to be induced in this coil through electromagnetic induction. You guys, if you have not subscribed to Proflearn YouTube channel, consider subscribing, so that when I'm going to do another tutorial, when you are going to join year 12, you'll be getting more tutorials of physics and pure math, as well as year 13. So explain why there is the voltage. Already I've mentioned there how that happens. When AC flows through coil P, it creates magnetic fields. When it flows through coil P, it creates magnetic fields which are constantly changing direction. When that magnetic field cuts through coil Q, an EMF is induced through electromagnetic induction. Explain why the core of the transformer is made of soft iron. Soft iron is a soft magnetic material which is easily magnetized and demagnetized, so it can be able to form a temporary magnet in that way, because a material that is required there is a material that can easily be magnetized and demagnetized. As far as transformer is concerned, the formulas that we need to know are these two. V, voltage in the primary coil, or voltage in the secondary coil, is equal to number of turns in the primary coil over number of turns in the secondary coil, or power in equals to power out for a transformer which is 100% efficient. And also you need to remember that power is voltage times current, so we can say from this formula we can say that power voltage in the primary coil times current in the primary coil is equals to voltage in the secondary coil times current in the secondary coil. So we are going to see how we can be able to use this formula in order to work out questions as follows here. So calculate the voltage between the two terminals of Q. So we have a number of turns in P and number of turns in Q is 340, and also we are told voltage in P is 4 volts, so we can be able to say voltage in P in the primary coil over voltage in the secondary coil is number of turns in the primary coil over number of turns in the secondary coil. So voltage in the primary coil was 4 volts. We are working out the voltage in Q, which is the voltage in the secondary coil. Number of turns in the primary coil were 200. You can see 200 here. 200 is indicated here. And number of turns in the secondary coil, number of turns in the secondary coil, number of turns in the primary coil is 200, which is indicated here, and number of turns in the secondary coil in Q is 340. So if we make VS, voltage in the secondary coil, subject of the formula here, we're going to have 6.8 volts. The heater is connected to coil Q, and the heater and the current in the heater is 3.5 amperes. So it means current output is 3.5. So definitely it's like this question here now is smelling. We are likely to be using this equation here because we have current, we have voltage, so we are working out the current in the primary coil. So we are going to say current in the primary coil times voltage in the primary coil should be equal to the current in the secondary coil times the voltage in the secondary coil. So we can be able to divide by 4 both sides, then we can have current in to be 6.0 or 5.95, which translates to 6.0. A bar magnet is made of metal. Suggest the metal from the bar magnet. A bar magnet, we're talking of a permanent magnet. It has to be made from a hard magnetic material, which is steel. We have two types of material, soft and hard. Hard are used to make temporary magnets, right? Then we are looking at the concept of electromagnetic induction. Here the diagram shows a bar magnet being inserted into the coil. So when this coil is moved, this magnet is moved in and out of the coil, the fields, because we are having here, whatever we are having here is basically we have the fields of the permanent magnet. When these fields cut across this coil like that, then an EMF is going to be induced in the coil. So this galvanometer is going to show a deflection. Explain why the galvanometer deflects. It's because when the magnet is inserted, the magnetic fields cut across the coil and an EMF is induced in the coil. Thus a galvanometer deflects. So if you move the coil faster, if you move the coil or you move the magnet faster, the deflection will be larger because a larger EMF is going to be induced. If also you use a stronger magnet here, there will be a larger deflection because a larger EMF is going to be induced. If you use more turns in this given point, you are going to have also a larger deflection. So basically you need to ensure that you really understand exactly what happens in this particular case. All right, so we really need to move to question number 12. We need to move to question number 12 here. We need to move to question number 12. And question number 12 is about what? Question number 12. What is it all about? What is question number 12 about? Guys, welcome to this tutorial where we are discussing about electromagnetic induction, an area which is quite very important as far as 0625 paper 4 is concerned, and we are in the section whereby we are talking about transformers, and in this case we are having a transformer here. But before that, on this question that we are having at this given point, you are really asked to explain what determines the direction of the direction of the deflection, the direction of the galvanometer. What determines the direction of this galvanometer deflection? What determines this? So the first thing that you need to consider when you are talking of that is the motion. In which direction is the magnet moving? The movement determines the direction. If it's moving in, the direction will be different as when it's moving out. Number 2 is the type of pole which is next to the coil, the polarity which is next to the coil. Those are some of the factors which determine. So we are going to say the factors that determine. Maybe if you are asked to explain the what determines the direction in the reading of the galvanometer is the direction in which the movement of the magnet is in, and also which pole enters the coil. Question number 12 is talking about a transformer. We are told a transformer used to allow lamp of different voltage rating to be operated from a 240 volt main supply that we are having here, because we have W, we have X, Y, and Z. Now, the primary coil and the secondary coil both have, the primary coil and the secondary coil both have 500 turns, uniformly wound in turns. Electro connection to the coil can be made. So we are supposed to calculate the number of turns between W and X. So what's happened? The lamp designed to light normal brightness at 120 volts. So we have a voltage in this case of 120 volts, and the the voltage input, voltage, primary voltage here, voltage in the primary coil is basically 240. You can see that. But the output voltage is going to be, voltage in the secondary coil is going to be 120. So we are going to use this formula. Voltage in the primary coil over voltage in the secondary coil is equal to number of turns in the primary coil over number of turns in the secondary coil. So voltage in the primary coil is 240, but number of turns in the primary coil, we were told both of them were having 500. So in this case, the number of turns in the primary coil we're going to use here is 500. Should be equal to the voltage in the secondary coil, which is 120, over number of turns in the secondary coil, which we are trying to determine. So if you work out the number of turns, you are going to get it to be 250 in this particular point. Then we are supposed to describe and explain what happens to the lamp when it's connected to X and Y. Let's look X and Y. What's happening between X and Y? We are having very few turns. So which means the number of turns in the primary is more than the number of turns in the secondary. So less EMF is going to be induced in the secondary, so which means that there will be less voltage, and the voltage is the one that determines the brightness of a bulb. So we are going to say that in this case, since it's connected in XY, there will be a reduced brightness in the lamp, since X has fewer turns, and hence less voltage is going to be induced. Then we are supposed to state what will happen to the lamp if connected to WZ. Let's see what's happening in WZ. We have such number of turns. They are going to be 500. If they are 500 and we are having also 500 here, we are going to have the same EMF of 240. So if the lamp is operating at 120 and you are making it to absorb, to be connected to 240 and is operating at 120, it means this lamp is going to blow. It's going to blow at that given point. So also let me take this chance also to remind you that you can be able to access this PDF in our Patreon page. So you can be able to go to Proflearn Patreon page. You check the link in the description so that you can be able to go and access this